Now we're going to talk about fundamentals of parallel computer architecture, and this will be in two parts, this module. The first one is about coherence and consistency. First, let's define and distinguish consistency versus coherence. Memory consistency, that is the term that refers to the interface between the programmer and the machine, the contract between the programmer and the machine, and it defines the correct behavior of shared memory. It can be different at different abstraction levels in the machine, so we can have different kind of memory consistency model at the machine language, another one yet at the assembly level language, and then also different ones at the C or high level language levels. In fact, C++ and Java defines their own memory models so that they can be independent of whatever model the hardware implements. And this means that compiler and runtime systems and Java virtual machine has to make sure that they implement the memory model of the language rather than irrespective of what kind of model the hardware provides. So the memory consistency is also called a memory model. On the other hand, we have coherence. That's a hardware mechanism that makes sure that data items can be cached in multiple locations. We also talk about cache coherence or cache coherence protocols. And this also ensures propagation of data updates between cores, and this is crucial to implement efficient memory models. So many people actually use these two terms very sloppily and maybe interchangeably. But the memory consistency is about how the memory model should behave, and the coherence is the hardware mechanisms that can be used to implement memory models. So they are linked, but they are not the same thing. So we're going to begin talking about coherence, because that's sort of a simpler concept in this context. We're going to give an overview of what coherence is and then how coherence is implemented, then going on to how we can implement scalable shared memory, and finally we'll end up with something about memory consistency. So this is the programming model we want to convey. So the threads, they execute on cores. So we're going to assume that there is an operating system that schedules threads onto cores and that there is one thread per core. For the moment, this is what we need to know. And then we have a shared memory, a shared address space. This is where data is stored for the program. Also instructions, but that's sort of beside the point. The important thing here is data. However, we do not build machines like this. We build with several levels of caches, and for now it's sufficient to think about just one level of cache. But caches add more concurrency to the machine. So whatever the thread or core needs at the moment can be hidden inside a cache. If you're unsure about how a cache works, you should go and look at a tutorial about caches. So caches provide automatic replication of data. I'm going to show an example here where we have two variables. We have variable A and we have variable B. These two variables are residing in memory, and they are 0 to begin with. And then we have 3 threads that execute instructions. So we have one thread here, let's call it thread 1, and we have thread 2 here and thread 3. It's good to have names on them. And then let's assume that thread 1 starts by reading a variable A several times. It reads variable A. So it will have a copy of variable A in its cache. The next thing that happens is that thread 2 also reads A, and you will get a copy of A in its cache, and then thread 3 will read B and have a copy of B in its cache, and then read A and have a copy in its cache. In reality, we actually may have several levels of caches here, as indicated in the picture here, but it's for the purpose of this discussion here, it's sufficient to think about one level here. So at this stage in the program, we have only been reading A or B. There is nothing else to be done. And you have instructions executed in some global order by the threads. We haven't really talked about in which sort of order these reads are seen, and that doesn't really matter because reads, they do not change state, so the order of reads is not so important. But now comes the interesting thing. Thread 2, let's give them numbers again. Thread 2 updates A. What will happen? This is the crucial thing here. What will happen? Well, we're going to invalidate all the other cache copies. Invalidate means remove, take away, not valid any longer. Okay? Why? Well, that's because thread 1 and 3 may want to use the value of A, and then they should have the new value that thread 2 writes to it. So thread 2 can then update. The numbers are keeping disappearing, and then thread 1 comes back and wants to read A again, and then it should get the new value from thread 2's cache. The cache memory system has to make sure that memory does not answer, because that memory has an old value of A, but the new value comes from thread 2. This is called a cache-to-cache transfer. Cache-to-cache transfer. Okay? So to sum up coherence, so this sort of basically shows what coherence is all about. But summing it up, there can be many copies of a data, but only one value. In practice, this is sort of good intuition, but it's too strong a definition. You can also see it as there is a single global order of value changes to each datum. So let's say thread 1 sees these changes to datum, and thread 2 sees these changes. It's a partial order. It's not a complete set, but it's a partial order. It's the same order. And then thread 3 sees these changes. This is not at all the same as here, so there is not the same thing here. So this is not the correct thing. If this coherence works, it means that after the computer stops, all copies should have the same value. So in modern day processors, where does coherence matter? Well, this is a picture of an 8-core machine where I have 2 threads per core, 2 hardware threads per core. It's a sort of a standard Intel Core i7 architecture or something like that. We have 3 levels of cache memory. We have the level 1 caches here, we have the level 2 caches here, and we have the level 3 or last level cache here. Level 1 caches are private per core. You have divided into data and instructions. Level 2 cache is private per core, but it's unified between instruction and data, and level 3 cache is shared per core. And then you have connections to other cores or other processors through the quick path interconnect, and then you have connection to the memory interface here. So where does coherence sort of, where in the machine, where in the processor is this implemented? Well, first of all, between the L2 caches on chip. These caches need to be maintained coherent. If the cache memory system implements something called inclusion, this means that whatever resides in the first level cache, it also resides in the second level cache if you have inclusion property. Then you don't have to deal with cache coherence at level 1 level, because if you invalidate something in the level 2 level, you have to make sure that it's invalidated in level 1 level also. You can never have anything in the level 1 that is not present in the L2. So here, at this level, you have coherence on chip. What if you build a bigger machine with several processors? Well, then the coherence between chips will have to take place at the quick path interconnect, or hypertransport if you have an AMD processor, or whatever processor you're having. So this is where the coherence protocol resides in a processor. To sum up coherence, coherent shared memory program model requires coherent. Otherwise, you'll have multiple copies of multiple copies of data values in the private caches of processors. You can build non-coherent shared memory machines, single-sided MPI or partition global address space or PGAS models, or other kinds of non-coherent shared memory models, but they are not sort of, it's difficult to build sort of, a C++ threading model on top of those. With coherence, all threads can read and write shared data, just loads and stores without any sort of discussion about that. And coherence provides a coherent view of the value of a datum, one data item. Okay? And in fact, it's even worse than this. It's a data item that fits in a cache. I can't spell here, so I have to take away this. Fits in a cache line. Bigger datums can't be protected by coherence, but come to why later on. And most often, coherence is kept per cache line.